Welcome to the Research Symposium of AI Week. It's great that you all arrived. I would like to thank you. And I'm Amitai from Intel's Advanced Analytics Department, and I would like to invite the chairperson of our first session, Professor Shie Schwartz from the Hebrew University and CTO of Mobileye. Please, Shie.
Thank you, Amitai, for the organization of this great event. So welcome to the Research Symposium. With this intimate atmosphere, you will feel the research. You can ask questions at the end. And I would like to welcome our first speaker, Professor Shie Mannor from the Technion, that will talk about reinforcement learning for extended intelligence.
So I see the slides, but you don't. Anyone help here? Oh, okay. Thank you. So hello, everybody. My name is Shie Mannor. I'm from the Technion, also affiliated with Ford and G3 Energy. I'm going to talk a little bit about RL, and as a good scientist, will be a pure technical talk. So this is a classical RL model that we've seen over and over in the books. This is what we teach students in RL 101. There is the model, which is usually a Markov process or Markov style process. There is an agent here, which is what we're trying to learn. There is some entity which we're trying to control. The agent has some actions it can choose from. It observes some things, and it gets a reinforcement signal, say the reward. Classically in RL, we see that we know the state space, so we know what we can observe, and we know what we can do. We know the actions, but we don't know the transition, and we don't know the reward. And classically, what we're trying to do is we're trying to find a policy. That's, I think, my only equation here, almost the only equation in this talk, that is will try to maximize the expected cumulative discounted reward. So this is classical RL. This is what we teach our students, and this is what doesn't really work. So, but it does work for some problems. So this is a famous Go application. The system that is being controlled is Go. Below you see the controller. The controller is a massive, multiple gigawatts compute center. It observes the state. It gets reward of 0, 1 if it wins or loses, and it can move the stones on the board. So this is what RL is mostly known for. And people say that RL is hard, and those are usually the three reasons that they give. So RL is hard because, first and foremost, because of the temporal create assignment problem. So I get the reward only a fairly long time after I actually do the action that led to the reward. So imagine in chess, somebody did something brilliant in step 4 of the game, and then he won the game. But it's pretty hard to figure out for a layman why the step in stage 4 was so brilliant, and to assign the right credit. So that's the first problem of RL. The second is that of exploration exploitation trade-off. So basically, I want to get from there is a nice maze here, and I start at S, and I reach G, which is the goal. And that's something that I can try to do. I need to balance between exploration, meaning looking at my state space, figuring out what's there, and exploitation, that is going in the fastest way. Exploitation is notorious because if you don't do it right, then it's going to lead to give you a suboptimal policy. So really don't know how to do it, but we can write many papers on it. So at least there is some win here. And last but not least, there is a curse of dimensionality. Basically, I can view state space in different levels, This can be the same state space as we have here, but now I have many more decisions to take, and the state space can become larger and larger. So it will take me longer and longer time to actually do anything which is interesting, just because I'll keep exploring and I will never get to anywhere that is interesting. So those are the classical three problems of RL. I believe we know how to solve all of them, and I believe that we're solving the wrong problem. So let me just tell you what happened in the last few years. In the last few years, this is a taxonomy of RL algorithms. There are many, many algorithms. Each of them, of course, deserves its own talk. So we have many algorithms, but very few real-world successes. And as a researcher, it's always nice to be able to write a new algorithm because I can get another paper out of it. But still, the real-world successes are not abundant. And here are some major successes. So we see here the StarCraft, Dota 2, and AlphaGo, and AlphaGo even got a movie, so this must be a great success. And it's on Netflix, by the way. So those are some major successes, but those are not real-world problems. All of them are isolated. All of them are problems that work without interacting with other humans, unless they're adversarial. And I would claim that while they advance the state of the art in the field, we have not been able to solve the major challenges yet. So some real-world successes. By real-world, I mean where money is spent. So I think the biggest success of RL is in recommendation systems. And of course in trading. In trading, as you see, there is a black hole because I don't think we'll ever know if somebody is really successful. So that's why it's a black hole. And then basically, at least to me, there aren't any other major successes of RL. And I think the main question is why. So why don't we have major successes? And before I'll go into details, I'll briefly talk about an RL problem which I've been working on. So this is a self-driving car. There are many companies, including some here in this conference, that work on this problem, but it's not such an easy problem. It's not clear how you define the reward, whether it's money, time, or energy. It's not clear what is the state of the observation, what do I see, know, or measure, and it's not clear what are the actions. So what can I do, and whether eventually all control is steering and brakes and throttle, but there are other ways to think about the actions. For example, maybe I'm going to overtake another car now. So this is an example for another problem. It's very complicated, and I think everybody would agree with me that we're not that close to solving it, in spite of investing a lot of time and effort in it. So one of the reasons is that there is a reductionist fallacy. And if you want to read one book about pseudoscience, then I recommend the book on the right, Resisting Reduction by Shie, the former MIT Media Lab director. This is written here. So basically, you would agree with me that only smart people play Go chess very well. You would agree with me that everybody can tell a joke. Computers are definitely very good in Go and chess. Therefore, the only logical conclusion that computers can easily tell a joke. I don't know if you've seen a joke generated by the computer, but it's not funny. So basically, we think that problems are easier, and because some problems are difficult for us, for example, playing Go, we think that, and they're easy for computers, so we think that those problems will be easy for computers as well. And that's just not true. So what I'm arguing is that we're solving the wrong problems that we think are going to be easy for computers because they're easy for us, but they're not. So maybe we can go all the way to AGI. And then when I was a student, my dream was to build one of those three. I'll let you decide which one. And we think that robotics are great and they're going to save the day. But I want to remind you that this is the state of the art in robotics. Okay, this is what we know how to do at the moment. So this is our level in terms of ability, and the application that we're having are roughly with this complexity. So this is not good, but funny. Okay, So what is the problem? So the problem is that our RL framework is data hungry. So to solve Go, it is said that the amount of compute power that was needed and the number of games that were actually played was about 10 times the number of games ever played by any human ever. And the amount of power that needed was enough to power a few small cities for a year. Our algorithms are opaque. We don't understand what they're doing. We don't understand why they're doing what they're doing. They're narrow. We plan algorithms that would work for very small, very particular problems. And last but not least, the algorithms are brittle, meaning that they're easily to break once your assumptions break down. And if you want, you can look at there are many people bashing RL and explaining why it's not working. This is just one of those blogs. And there are many others, trust me. I think we have to make a distinction between the types of RL problems, and there are three types that I'm considering. This is a Pac-Man, so there is a Pac-Man is here, and Pac-Man wants to eat all the fruits, and there are the ghosts that are going to eat Pac-Man. So there are static problems. In a static problem, Pac-Man is alone in the world, and there are no ghosts. So this is a problem where there are no other agents, and you can just do whatever you like. Those are usually easy problems which we know how to solve very well. Chess, in some sense, is such a problem because we all know that the other player is going to be adversarial. There are dynamic problems. In dynamic problems, there are ghosts, but the ghosts don't care about what Pac-Man is doing. So the ghosts are just there. There are other agents, but they don't really care about anything. And then there are counterfactual problems. Counterfactual problems are the only real problems that are interesting. Because there you have Pac-Man and you have the ghosts, and the ghosts react to Pac-Man, and Pac-Man reacts to the ghost, meaning that whatever you do, other agents are going to react to you. So for me, we know how to solve static problems very well. We are pretty good with dynamic problems, and we're not that great with counterfactual problems. And counterfactual problems are what is really interesting and what we need to solve. So with other people, we're looking at something which we call extended intelligence. So this is much more meager and poor man's version of artificial intelligence. So instead of trying to solve very complex problems, we just want to solve problems where we have a system that participates as a part of an element of a more complex system that needs to discuss, to communicate with others. So the picture that we have here, that you have the controlling agent, but it's going to talk to an extending agent, whether human or not, and with other agents. And while you're still using the same actions, the controlling agent has to be aware of itself being in part of a much larger system. So think about it like the difference between driving a car that drives on its own and going on auto cruise mode. So basically, you can stay on auto cruise mode for a while, but eventually somebody's going to take the helm from you. So I claim that extended intelligence is where we should be heading. And I think that this is, there are 5 design principles. And I emphasize the word design because the way you should think about it is not from the point of view of the researcher, but rather from the point of view of the user. Think about the control engineer or someone who's actually going to use it. And the 5 principles that we've been looking at are awareness, meaning that you know how well you perform, you can communicate what you do, and you're cognizant of everything that is happening around you. Basically, you know what's happening to you. The second is accountability. So accountability is much more than explainability. You're not only able to explain what is going on and what you're doing, but also you can give examples or maybe do some calculations and explain what is happening there. Then there is adaptivity. Adaptivity means that you function even when the system is not as described, and you have an algorithm which is not as brittle as classical RL. And then there is an issue of lifecycle consciousness. This is a very important issue because debugging an RL system is incredibly difficult. If you've ever tried to build a system, then you know that debugging it is just not going to be fun. So you need to build systems and algorithms that can be debugged, can be tested, can be verified. And last but not least is scalability with resources. This is sort of something that we have to do. The more data, the more compute you have, the better you think your algorithm should perform. And that's how I think about RL problems. So I look at the different axes, the 5 axes of extended intelligence, awareness, adaptivity, accountability, life cycle consciousness, and scalability, and I map what I'm doing to those axes. What we're going to talk about now is going to talk about robustness. And robustness is something that I map to, very important to be adaptive, because that's the goal of robustness. Very important to be scalable, a little bit of awareness, because you may want to know once you're away and off the charts, and a little bit of accountability, not so much helpful for life cycle consciousness. So the way I think about research is along those 5 axes, which one are served by the research question at hand, and therefore we look for less for algorithms and more for solutions. So I'll give you an example from a recent paper from a group. And in this example, we have a policy which I have a policy, but my model is not that great. So you can think about it like a trembling head model. So my hand is shaking. I want to choose policy pi, but what really happens is somebody is going to choose pi prime against me, and then with small probability of alpha, this pi prime is going to be chosen. And there's nothing much I can do about it. But I know that alpha is not large, and I can choose pi any way that I want. So this leads to an algorithm which we called action robust DDPG, and it's really kind of a natural way to think about guns in RL. So the algorithm is like everything else in life, has 3 parts. So I find an optimal actor policy. I look for the adversarial, the worst possible policy against it, but only with a small probability of alpha. I evaluate the joint policy, and I do this in cycle ad infinitum, or until convergence, or until the deadline of the conference. So basically, I do this continuously, and I always try to find the worst possible pi prime policy against my current policy. And this is just to show you in terms of performance. So this is a graph which is, this is not 2 domains. We have many other domains in the paper. This is Hopper, and those are Walker, those are Mojuku domains. And what you see here is that there is the probability of the noise. So this is a more difficult Hopper. It's like a Hopper that gets pushed all the time, and same for Walker. So there is a probability that you're not going to succeed. And then there is a relative mass, which is relative to the original mass, which is 1. And here is the mass is 1 as well. So basically, this is a classical problem, this point here, 1 and 0. And everything else has just noisy versions with heavier or more noisy domains. And what we see is that yellow is good, red is bad. Naturally, like in any research paper, our algorithm works great, but we see something which is interesting. So it's not only that it works better across most noise probability and relative masses, but also, and I think interestingly, even for the original problem, it works better. So even when there is no noise and you're actually trying to solve the original problem that you could solve with your favorite algorithm, once you inject robustness into it, then you get superior performance. And that's a theme that I think some of you know I've been working on for the last million years, which is robustness equates generalization, robustness leads to generalization, and we see here it in a very strong way. So even when you solve the original problem, once you solve a robust version of it, then you get better performance and you generalize better. So for this short talk, I'm almost done. But for me, RL is a combination of 8 things. So you can write many papers on the different combination of those. RL is data, it's representation, it's algorithms. I think we're pretty good there. But it's also awareness, accountability, adaptivity, lifecycle consciousness, and scalability. Think that if we have algorithms that we cannot debug and are not aware of their performance, they're not going to get very well. I mentioned that some people ask me, like, when are we going to get full autonomy? So the answer is very far. And just to remind you, RL works best when you have a very stochastic environment, when you have high throughput control, or a lot of data, and the problem is not counterfactual. So the other agents do not react to what you do. But the real world is neither of those three, so there are still many years of research to come. So with that, I will conclude. Thank you.
Thank you very much. We have time for a few questions. I can't see anything, so just shout.
Okay. You see something? You want me to ask? No, you don't have to ask anything. It's not.
Why are you classifying the game-based examples as non-manufacturing?
Sorry?
Sorry.
Please repeat the question. It was not.
Why are you classifying the game-playing examples as non-counterfactual? Aren't the other players trying to beat the algorithm?
Right. So if the other player is adversarial, then it's not really counterfactual. When the other player is predictable, predictably adversarial, it's more of a dynamic problem. If the other player has its own agenda, like say pedestrians crossing a road, then it's really counterfactual. But counterfactual means if the adversarial problems are relatively easy, also the math works very well because you get contractions all over, so that's a little bit less interesting.
How much of accountability part do you, like the value comes from the debugging capabilities that is allowed? I will repeat. About the point of accountability that you mentioned, do you feel the biggest value is from the capability of debugging that it should allow, developers like us, or let's say to make humans feel more comfortable with the decisions that they get?
So I think both. For me, at least, most of the value comes from making humans feel more comfortable. In my lab, we have been working a lot with doctors in the last few years. Being semi-gods, they would not allow anything that is not explainable and even something that they can reason with. So I think that for us to move to some real-world domains, we have to be explainable, maybe by example. So you don't have to explanation doesn't have to be textual, but maybe you'll say this is like some other patients that we saw some time ago.
Thank you very much. Thank you. This was a great example of adaptivity to the time.